Okay, thanks. Good morning. My name's Lorraine Fesq, and I'm going to talk to you about developing a guidebook to do fault management for deep space robotic missions. And you may recall a few years ago I presented a handbook, NASA handbook on fault management. I'm going to refer to that. I have a little bit of egg on my face from that talk, but for good reason. So I'll get into that in a bit. But why are we talking fault management at a flight software workshop? A lot of the fault management portion is implemented in software. Some of it's implemented in hardware. Some of it's implemented in software. And on some of more capable missions, like our deep space missions, especially things like Cassini and our larger flagship missions, over half the flight software was dedicated to fault management. So I think in that case, it's very relevant to be discussing fault management at a flight software workshop. So what do we mean by fault management? Really, it's the addressing how to handle faults so that your mission doesn't end due to one anomaly, due to a fault, due to a failure. And this picture depicts all the different types of missions that we have at NASA, and all of them attempt to address faults, but they have done it from a different perspective. And so fault management has kind of grown up in a number of different ways through these different communities, if you will. In fact, it has different names. It's sometimes called integrated system health management, fault protection, integrated vehicle health management, redundancy management. I saw an autonomy on the last presentation. I wonder if that was handling faults. I don't know. Fault detection, isolation, and recovery. The human space flight world calls it, they address it through hazards, aborts, cautions, and warnings, as well as FDIR. And then there's health usage monitoring systems. So all of these are really capturing an element or the essence of fault management, but doing it in slightly different ways. So back in 2010 timeframe, we had presented the results of a workshop of a fault management workshop. It was the first NASA fault management workshop back in 2008. We presented that to the chief engineer at NASA. And what that workshop had exposed was just how diverse this field is. And he charged us to coalesce the field, try to bring it together. I mean, there really isn't a textbook on how to do fault management, similar to how there's one for how to do attitude control. There's Jim Wirtz's book on attitude determination and control, or even his SMAD book. But there isn't one for fault management, and so we kind of do it how we feel is the right way to do it, and we end up with a lot of different approaches and different products. So the goal back then was to coalesce the field by putting together a handbook for all of NASA, and here's how you do fault management. And one of the impetuses for doing that was that most often we develop monitors and responses to address faults that we can think of ahead of time, and then we get into integration and test, and we have a big collection of fault management monitors, and it's very hard to test them all in all the different state space possibilities. And there were a number of missions, I think it was 5 missions in a row back in this time period, that were running into scheduling problems. They couldn't get through the test program for the fault management portion. So, and it wasn't anything in particular with the deep space or Earth orbiting or contracted or in-house. It just seemed to be a pervasive problem. And so so we wanted to really improve the reliability and safety of these missions and get a handle on how we do testing of them. So we made this attempt to write a fault management handbook, and we outlined it to address the needs of the agency, but the funding was coming from SMD, so it was very much tailored to the deep space mission or the science missions. And we looked at it as a companion to the systems engineering handbook. So we released that handbook back in July of 2011, and we received over 1,000 comments on it across the agency, which is interesting. I mean, it shows that we hit a nerve. it was a record for the NASA Tech Standards Program Office. They had never received that many comments on one document. And on the right, I have a chart of where the comments came from, which center had the most comments. Thank you, Ames, if you're here. About 500 of them were due, I think, to the handbook not representing all these diverse views across NASA. So, so I took a stab at dispositioning some of them and released a draft 2 in 2012, and that's the one that still sits out there. But one of the key things I noticed was a lot of the comments were inconsistent, and they were inconsistent even within the same community. Let's say the deep space community, or the robotic Earth orbiting community, or the human spaceflight community, or the launch vehicle community. I was getting comments that just I couldn't resolve in between the two comments, say. So it was a very painful process. But I think what that whole adventure did was it uncovered just how diverse this field is. And I didn't feel that I was qualified to disposition all these comments. I didn't even think one center really was in a position to disposition the comments. So instead of trying to bring everybody together in a kumbaya session and say, here's how we do fault management, I felt maybe we needed to back up and say, okay, within each community, we need a guidebook on how to do fault management. So that picture, that slide that showed all the different pictures of those are the different communities. There's the launch vehicle community, the human spaceflight robotic community, the aeronautics community. If one community could come to consensus on how they approach fault management, then we could even put those in as chapters of the fault management NASA-wide handbook and start to look across and understand what the commonalities are, what the differences are. And maybe we don't all do it the same way, but at least we can start to understand how each of us does that. So that brings me to my current activities of developing, now with all these qualifiers, the Deep Space Fault Management Robotic Guidebook. Okay, so now we've scoped it down. So we're just going to say, here's how we believe we should be approaching fault management for this particular type of mission. And we looked around and we noticed that there really wasn't even a guidebook in existence today for how to do that. We often rely on people who have done it on past missions and use architectures and designs from past missions, even if they may not quite match, but we used it on the last one, why not use it on the next one? So we have kind of an ad hoc approach to doing fault management today. And this guidebook was also intended to address some of the issues that came up with developing the NASA-wide handbook. We intend to host it on the NASA Engineering Network Fault Management Community of Practice. If you're interested, I have a link at the end. But you can just go on then, if you're inside the firewall, and find there's a number of communities of practice there, including fault management. And we intended to leverage a lot of existing guidance, not just start from scratch. But we have, at JPL, we have design principles and flight project practices, and we have group-level documents. And we really wanted to add more of how to do fault management, not just what is fault management, which was what we were seeing in other field guides. This is currently being funded by our Office of the Chief Engineer. And just to put this in perspective, there are a number of other organizations out there that are doing similar activities. APL, a few years ago, pulled together a fault management engineering process. The SAE has formed a committee, an Integrated Vehicle Health Management Committee, to develop a book that they're calling a standard on IVHM, looking at it as an emerging field. IEEE has a community that is developing a standard for prognostics and health management. It's a little bit more lower level at the electronics level, but they recognize the need for it. And aerospace has come out recently with a number of guidelines. One is the effective fault management guidelines and a proposed safe mode standard for satellites. So we're trying to wrestle this beast to the ground in a number of different ways. So what is in our guidebook? So our guidebook starts with a very high-level process, which looks pretty generic. I mean, you can use this for any subsystem, really, but laying out a high-level process of the mission life cycle, what the phases are, what the key milestones are, and then the activities within those phases. And then for each phase, we have developed something that we're calling a spider diagram because it just looks pretty messy. But what this is the main boxes. I don't have a laser pointer, do I? The main boxes on this are tasks that need to be performed during a particular phase. And you can see the little, if you remember flowcharts, the document sign. The documents coming in, there's products coming in that are needed to perform that task, and products that are outputs for those tasks. So every task has inputs and outputs, and some of the tasks are even color-coded, some of the documents are color-coded as required for a particular a gate product. This one's due at PDR or CDR or whatever. And then the relationships between those tasks. So we took each phase and laid out a spider diagram, and we're still developing this now. We're in phase D at this point. Oh, he's got a laser pointer. Cool. Okay, so these larger boxes are the tasks, and then this one pretty.
Could I recommend you move the mouse? That way it gets recorded. Thanks.
Alan, you're good. Okay. So for example, here's this box here is a task, and the output is a product that then feeds into another task and comes out with another product. Okay. And then this is a blow-up of one of those boxes. So for each box, each task, we're describing what the task is. So this is developing an initial fault tree or event tree. So based on your initial level 3 system and fault management design, develop a mission fault tree for each identified key mission scenario. So what is this task? Why do you do it? What's the objective? That's here. And when is it due? It's a project milestone in pre-phase A, and you need to complete it before MDR. Here are the inputs, the lines coming into that box. Here are the steps that you need to complete. And it looks a little pedantic, but these steps are not that low level. They're pretty high level. So here's how you do the task. And then what is the deliverable coming out of it? Why are you doing this? What are you going to be producing? And then these deliverables, we might have examples from previous missions or even a template. Here's what we expect to see at the end of this task. You shall produce this product. And this is an example of one of those products. So here we're showing an example artifact or a template. So coming out of this particular task, you'd like to see perhaps a table that shows your fault coverage. So here are the different faults, and then the cause of the fault, how a fault injection method, how a fault might be injected, what's your mitigation. So if you can lay that all out, that's the end product for that particular task. So it shows starting with a high-level flow, going into your task, and going all the way down to an example of what the product is that's coming out of it. And we're looking at this to be very navigatable. So if you clicked on the bottom, you could return to your previous task. So looking at all of that in one slide, you go from your overview of the whole fault management process. You zoom in on the spider diagram for a particular phase. This is phase A. You zoom in there on a particular task, and which describes what the task is, why you do it, inputs, outputs, and what the steps are, and then even some examples of deliverables, either an example from a previous mission or a template on what we think that product should look like. So this really does pull from past experience and lets us codify, if you will, how we do fault management. So we look to this product to be a field guide for engineers. So if you're a new fault management engineer on a mission, you can pick this book up and have an idea of what you're supposed to do. I'm not sure that exists today. Usually you have other people that are helping you, telling you what you need to do, because we don't really have this written down anywhere. We also see it as a manager's planning tool. So managers have expectations now. They can see, at PDR, these are the products that I should get from the fault management engineers. And help to keep you on track schedule-wise. I look at this as the deep space robotic chapter of the Fault Management Handbook. So eventually, this is the first of its kind, and eventually if we can get the other communities to write down and codify their approaches to fault management, then we can start pulling together the NASA-wide handbook on fault management. And then this also would be a companion to the NASA Systems Engineering Handbook, as well as the Software Engineering Handbook. So we plan to complete this early next year and post it on this NASA Engineering Network, on the Fault Management Community Practice. And here is a website if you haven't been there yet. And I think that's all I have. Yep, that's it. Questions?
We can take questions.
Jonathan.
Hello. Any thoughts about how the information is going to be compiled? Because before we were using the standard NASA Word document structure, which is really difficult to use. I think different communities and organizations are going more towards web-based, SharePoint-based, so you can do that kind of interactive. So one question is, does it have to be formulated into that structure, which makes it more difficult to use, or are you thinking about going to something else? And the second, related to the earlier presentation, where we had comments about avoiding too much planning so that we can allow innovation. One of the concerns, of course, with an organization is we want a standard, we want training, but we don't want it so hard-coded and so detailed that now you just have to do these steps, and which becomes difficult to scale as you move into, as you try to be lean. So
Right.
Kind of those two questions, how to compile this so it's usable, and is there any thought about how to make this scalable to, maybe it's training instead of a handbook. Maybe you're just trained on what fault management is so that you can go into a small lean team, or how do we balance those two things?
Yeah, really good question. So the first one, we decided not to do a Word document, and we're developing this in PowerPoint that we intend to put onto the web and make it web searchable. But if you don't have access to the web and you want to be able to maneuver and navigate through it on your own computer, you can use the PowerPoint version. But it's just for ease of us developing it, we're using PowerPoint. And part of the reason is that we want to keep it at a high enough level. We don't so that we're not being pedantic. We're not prescribing every last step. So right now we have, the concept is just get this in PowerPoint and then move it onto the web and make it navigatable there. The other cool thing about doing it in PowerPoint, even though you might not like PowerPoint, is that we now have our training material. So we're developing our training material along the way, so we can then just take this package and go out and work with our engineers and give them an idea of how to do fault management. Okay, second question had to do with...
It was related to that, yeah. Is there, I guess if you don't have it in a standard NASA document, it becomes harder, to be over-codified or forced to allow training. But of course, the training requires not just a PowerPoint, but a product set or something, because you can't really learn from just PowerPoint slides.
So, and let me take that off on a tangent a little bit, because one thing we struggled with here is that we want to lay down enough landscape to allow people to get to know what the job is, but we don't want to be prescriptive. And we want to accommodate Class A versus Class D missions, right? And so the way we addressed that was, this is scalable. People can use as much or as little of it as they want. A lot of the documents that were on the spider diagram, we have color-coded, some that we really think are very important. Others, if you're a Class D mission, you may not be producing this, or it may be part of a system engineering document, you know, but it's not definitively you must produce this document. So it's really hard to write a guidebook for everyone. And the way we addressed handling the different classes of missions was at one point we went in and for each of these tasks, we put a percentage on it. So, for example, for this big task in the middle, maybe that had like a 35% on it. And what we meant by that is during Phase B, you're probably going to spend about 35% of your time, whatever that time is, whether you have a team of 10 or half an FTE, right? But you're probably going to spend the most time here. And that's the way we were trying to accommodate the different sizes of missions. So what we're ending up with is really a codification of what we think are the best practices, and you can use it however you see fit, however you have a need. I probably didn't answer all of your question, but we can talk later. We have another question back here.
And you mentioned that URL was behind your firewall, and then you said that this was going to be published out on the web. So will this information be available to those of us in the...
If you're on a NASA mission and can get behind the firewall.
Okay.
It'll be on this website.
Yeah, that's not us, I don't think, even though we're an NASA mission.
So if you're a NASA mission, you can't get to the NEN? Then... Okay. Yeah, I would hope so, because I think it's available to all contractors as well.
Okay, Kelly, do you have a question? I see you raised your hand. You don't. Any other questions?
Since this is a really software-focused conference, a lot of the concepts we talked about here are a little bit higher level and system level. Do you have any specific takeaways for software engineers when they look at this? You know, when I look at this as a system engineer, I understand what it's telling me, what I'm going to do with it, what I'm going to provide to software engineers.
Yeah.
What's maybe a key takeaway for software engineers? What do they need to know from this as they move into their model-based development and as they interact with pushy system engineers?
I'm glad you mentioned model-based. I would actually love to see this field move in a model-based direction. So the field right now, I think of as a field of Band-Aids. So you've got your nominal design, and then you think about, oh, if this fault happens, then do that. If this fault happens, then do that. And you can think about all these monitors, these if-thens, as a set of Band-Aids. And that's why when you get into integration and test, you end up with a bucket full of Band-Aids that's really hard to test because they can interact with one another and overlay one another and interrupt one another. So if we could move this field to a model-based approach where the software engineers are encoding models of how the hardware is supposed to work and comparing that to the actual measurements on board, it's a much more systematic fashion. But when we were developing this, we kept struggling with, do we want to codify how we do it or how we think it should be done? And we walked a fine line there. We kind of moved in what I would consider the right direction, but I still have a vision of eventually we need to get to a model-based approach to doing fault management and not this Band-Aid approach.
Thank you, Lorraine.
Okay, thank you.